numbers before? A couple of us. Okay, a few of us scattered throughout the room. So essentially, if I can get this zoomed right, here we go. So what are complex numbers? So far, you guys have learned that there's real numbers. And in this set of real numbers, there's a bunch of subsets within there. And that includes like the rational and irrational. So real numbers are split into two categories. The number is either rational or it's irrational. And then within the rational numbers, there's lots of other sets of numbers, right? Like that kind of get, I don't want to say smaller because they're all technically infinitely large, but within scale of each other. So what is a complex number? A complex number can be made up of a real number, but there's also another set of numbers we haven't talked about yet. So separate from the real numbers, there's another set of numbers called imaginary numbers. So if we were mapping it like this, this is where they would go. That all the numbers you've learned so far are real numbers, and we have a bunch of more specific names sometimes for certain numbers. Outside of the real numbers are the imaginary numbers, and a complex number can be made up of both of these things. So your real numbers were technically complex, but they could now also have an imaginary part. So this whole thing together, is the complex number system. Is that okay with everybody? So complex numbers mean they're numbers that include the real numbers, but they could also have this other part you haven't learned about yet called imaginary, and we'll talk about exactly what that is. Okay? So Descartes came up with this, and basically there was a need to get through some calculations that we couldn't get through in the real number system. So in certain studies, mostly in like electrical engineering is where you would see it in like current time, there comes a point where you can't complete the process without being able to do arithmetic with something that doesn't fit in our real number system. So you know how we always say you can't take the square root of a negative, it doesn't work, there's not a real number. So that's the calculation they needed to get past. So this is what Descartes did, and he's a very intelligent mathematician. As they came across this problem, he decided that he's going to define something. And you guys could all define your own number system, but unless it worked with our current number system in a logical way, like nobody would ever use it, right? Maybe you would because you were all proud of it. But his works hand in hand with what we have and helped get through this problem, which is why it was like adapted to be used. So he basically defined this, that I squared is equal to -1. So what he was saying is, guess what? I'm going to make a number that you do square and get a negative. Basically, that's what we need. We need a unit that squares and works out to be a negative. That doesn't exist in our real numbers, so I'm producing this other thing. So he called it I. And so I squared is equal to -1. And that's basically the only thing he had to define. So from there, that would mean this. That anytime we see the square root of -1, that would be equal to I, because he said that I squared equals -1. Is this okay with everybody? So now the square root of negative can be expressed not with a real number, but with this I, this imaginary number that Descartes came up with. Okay? So just to get you used to the powers, we're going to look at it. And so we look at different powers of I. And then I want you guys to know what simplest form is. A lot of people see I and they rewrite it as square root of -1, but we don't want that, right? We used to come across a square root of a negative and then not keep going because that wasn't in the real numbers. Then we want to write it as an imaginary number. So if you see a negative underneath a radical, the simplest way to write it is to write it with an I. That's the way that we would prefer to write it, okay? What do you think is the simplest way to write I squared based on the definitions that we just talked about? What is I squared? How was it defined by Descartes? Look back at what's on your paper. I squared is equal to what? -1. See at the beginning up here we said I squared is equal to -1. So whenever you see a I squared, that really simplifies to be -1. Okay. This is why his system still exists and why if you made a number system, it might not exist. His system is tied in with ours. If I squared is equal to -1, even though I is an imaginary number, this system that he came up with, it works hand in hand with the real numbers because I squared is -1 and -1 is a real number. Okay? All right, what would be the simplest way to write I cubed? Morgan? Okay, so -I is how we would write that. Do you guys see that? So if I write out I cubed a different way, I cubed could be thought of as I squared and one other I. Oops, not I squared again. And what is I squared equal to? -1. So this is really -1 times an I, which ends up being -I. All right, what about I to the 4th? What's up? Yeah, normal one, or how about just positive one, right? So I to the 4th could be thought of as I squared times I squared, but what is each I squared worth? -1. So this is really like having -1 times -1, which equals +1. Okay. All right, what I want you guys to do that's not on here, so we just figured out we have I. Then if we have I squared, that's really equal to -1. We have I to the 3rd, that's equal to -I. We have I to the 4th, that's equal to +1. I want you guys in your group right now to think about what would I to the 5th, I to the 6th, I to the 7th, and I to the 8th look like. Okay? So in your groups, figure out the simplest forms of. So we want to look at the patterns we saw. Who can tell me what I to the 5th simplified to be? Yeah. Say it again. So I to the 5th would be like I to the 4th and one more I, right? What's I to the 4th? +1. So +1 times I will just be I. Okay. All right, what about I to the 6th? Brandon? -1. Are you guys okay with that? So a power of 6 is like a power of 4 and another power of 2. And a power of 4 is really equal to 1. And a power of 2 is really equal to -1. So it's like having a 1 times a -1. What about I to the 7th? Somebody else, what did you get? Morgan? So -I. So you guys, I to the 7th can be like I to the 4th times I to the 3rd. And again, your I to the 4th is like a 1. And I to the 3rd was like -I. And 1 times -I would be -I. And what about I to the 8th? Good, 1. Okay, it's like I to the 4th times another I to the 4th. Notice that the answers that these are simplifying down to, can anybody make a conjecture about any power that I put on I? Like without doing this problem right here, but like in part A, it says I to the power of 231. Could you at least narrow it down to like 4 choices that the answer might be if you evaluated I to the power of 231? What would your options be? What could be an answer? Brandon? Good. Basically, these things right here, right? I and -I, 1 and -1. Is that okay with everybody? That even if we keep raising powers, because these basic powers simplify the way they do, everything I'm multiplying either simplifies to a 1, a -1, an I, or a -I. So higher powers of I don't really exist. They do, but then they all simplify back down to either a real number, 1 and -1, or an imaginary number, I or -I. Is that okay with everybody? So that should tell you 2 things. 1, we're going to try and figure out these higher powers. And number 2, if you're simplifying anything with I in it, would it ever be simplest to leave I with an exponent on it in your answer? No, because every exponent we've looked at either simplifies back down to being 1, -1, I, or -I. So if you have anything in a problem with I raised to a power, there's a simpler way to write that, and we need to write that in a simpler way. Is that okay with everyone? All right, so what could we do? I don't really want to write out the 231st power of I. So we need kind of an idea of what we've been doing when we were getting these higher powers of I. So when you guys went and calculated 5th, 6th, 7th, 8th power of I, what did we do to kind of do that we can do here with this 231 as a power? Morgan? Good. Find something that's divisible by, right? What, when you multiply stuff out, doesn't change things when you multiply by it? 1, right? So I generally look for ones because if I can take all the ones out, it doesn't matter how many are there. Anything times 1 still ends up being itself. So having extra ones multiplying in just basically means I get to like ignore them, right? And what power of I makes ones? What power of I makes +1? 4th. Okay, so I basically want to figure out how many I to the 4ths do I have in 231. Okay, so I'm going to take 231, divide it by 4, okay, and it goes in there, let's see, 57 times with 3 left over. Is that okay with everybody? That means that I to the 231st power is the same thing as using I to the 4th 57 times. That doesn't quite make 231, right? How many did I have left over? 3. And then I have 3 more. And the reason I like writing this again is because what is the value of I to the 4th power? 1. What is 1 to the 57th power? 1. So this whole thing just becomes 1 times I to the 3rd, which is just I to the 3rd. And what's the simplest version of I to the 3rd? -I. Is this idea okay with everybody? So main point, like, I shouldn't be leaving I to any power in my answer. If I am, I'm probably missing something that it's worth. Okay? All right, so now, if we want to simplify things like the square root of -24, normally you would stop and say it can't be simplified. But now we are going to say it can be simplified. And the good news is that most of it is just like what you used to do. The only new idea is the idea of I. So we want to think of the square root of -24 as really being like the square root of -1 times the square root of 24. And how do I now express the square root of -1? I. Okay, so that's an I. And then the square root of 24, now that you've taken the negative away from it, you just break it down like you normally break it down. So the square root of 24 is like square root of 4 times square root of 6. Square root of 4 is 2. So I basically have a 2 times an I times a rad 6. So 2 and I will be written outside of the radical, and rad 6 will be written inside, and you'll usually see it written in this order. They usually don't put the I after the radical because I think it's hard to tell if it's like underneath the radical or not. It's a little skinny letter. Okay, so you write it like this. So you're still simplifying the square root of 24 like you normally would. You are just kind of honoring the fact that you understand there's a negative underneath there by including I in your answer. Is that okay? All right, so go to the next page. All right, so now when you go to solve things, anytime a negative shows up in the radical, you can keep going. You still have no real answers, which means would you expect to see x-intercepts if you graphed it? No, but you just have a different way to express your answers. Like I can't give you real answers, so I know it's not hitting the x-axis or anything on the graph, but I can give you a way I can write this It just has to be in a complex number format, meaning I is gonna show up somewhere, okay? So we're gonna actually look at, this one we just have to take square roots. So we're gonna actually look at part B, okay? So in part B, if I was trying to solve this quadratic, I would first try factoring, okay? But if it's not factorable, I would then move on from there. So the next thing I would try, you guys can either complete the square or use the quadratic formula. Any preference here? Anybody? Quadratic formula? Okay, it's fine. It's not the worst completing the square problem ever. But I get it. I don't normally complete the square that often either, don't worry. Noelle will complete the square for us and let us know how it goes. So underneath my radical, I get a 16 minus a 20. So I'm getting a -4 underneath my radical. Okay, and for that square root of -4, remember how I'm going to think about it. The square root of -1, which I need to deal with the imaginary numbers, and the square root of 4, which I know how to deal with, it's 2. And this is I. So my square root of -4 is going to be rewritten as 2I. And now you can simplify this like you normally would. The 2 is not underneath a radical. So this 2 in the denominator, oh sorry, it's a -2 in the denominator. This -2 in the denominator can divide both terms of the numerator that it's a denominator for. And I'm going to go ahead and continue simplifying that way. So the first thing I'm going to look at is -4 divided by -2, which is 2. And then I'm going to look at this, and the plus minus might throw you guys a little bit, but let's say it's a positive 2I and then it's being divided by a negative. What's a positive divided by a negative? Negative. And then what's a negative divided by a negative? Positive. So we still have a plus or minus here because the negative would just turn the positive to a negative and the negative to a positive, okay? But we'd still have both. And 2 divided by 2 is 1, and they can cancel out those real parts, and then we just have I. So these are our two solutions. You wouldn't see them graphically hitting the x-axis because your graph is only measuring real number units. So when you don't have real solutions, you can have imaginary or complex solutions, but you won't see them crossing the x-axis because it's numbered by all real numbers. Okay? Is this okay with everybody? So same processes as before. You just don't always stop when there's a radical underneath a negative. You're going to express it as a complex number. All right, and then how the complex numbers basically work. We want to be able to add, subtract, multiply, and divide with them and just make sure you're comfortable with it. The good news is there's not some new magic multiplication or something like that. You just have to really deal with the powers of I. So if we are adding, we are combining like terms. So real parts combine with real parts and imaginary parts combine with imaginary parts. And what I mean by that is when you guys look at this 2 plus I right here, that is one complex number, but that one complex number has two parts to it, right? It has a real part. The 2 is completely real. It doesn't have I attached to it. And then it has an imaginary part, the part that does have I attached to it, okay? Then there's a second complex number over here that again has a real part to it and an imaginary part to it. So you combine real parts together because we know how to add together real numbers. So 2 plus -3 makes -1. And then the imaginary units combine together just like we add real numbers. So 1I plus 3I would make 4I. Is that okay? All right, so think about it a lot like combining like terms. Okay? Real parts with real parts, imaginary parts with imaginary parts. So when we get this subtraction problem, really the only difference is that that subtraction, just like when we were combining like terms in Algebra 1, we have to remember that that subtraction sign applies to all parts of the number that follow. And so our real parts would be -6 and -4, making -10. And our imaginary parts would be -2 and another -2, making -4I. And then the last two are multiplication problems, and they multiply the same way you would expect anything that looks like this to multiply, just like you guys multiply your binomials together. So you're foiling or using the distributive property. So this real 5 is going to multiply each term in the next complex number. So I'm going to get a negative 20 minus 15i. And then the negative 7i is going to multiply each term in the second binomial as well. So you would have plus 28i plus 21i squared. Is everybody okay with the multiplying step, that it looks just like your foiling or distributing property? Then we want to combine like terms. So right here, these two terms are both imaginary parts. So we have a negative 15 plus a positive 28. And so those will add together to make positive 13i. And actually, the negative 20 and the 21i squared are both real. Even though you see an I with the 21 squared, how come I know that it's a real number? Good. I squared is actually equal to negative 1. So what does 21i squared really mean? Negative 21. This is really 21 being multiplied by negative 1, and it's a negative 21. And that's going to be combined with that negative 20 to make negative 41 plus 13i. Is that okay with everyone? So the operations aren't that different. It's really just the simplification, like knowing the powers of I really well and what they mean is going to be the key for you to be able to simplify them. So D is just like part C, but what's going to work out really nicely in part D? Why did I put 2 multiplication problems on our examples? Why would I do that? What's my motivation here? Nothing, I just wanted you to do more multiplication. So yeah. Good. The i's will cancel out. D is special. It's your sum and difference of squares, right? So you're going to see this 16 plus 12i, but then you're going to have minus 12i, and then minus 9i squared. So all the imaginary parts are canceled out, and you're really just left with 16 plus 9, because remember, this is like negative 9 times negative 1, which is 25. Never seen such 2 crazy factors that multiply together to make 25 before, right? Yeah, there you go. All right, and then the last thing we have to talk about is the division, or when I shows up in a quotient or division problem, which it is here. And technically you don't have to do division, but these are not written in a proper format, right? So what do we say whenever there's a radical in the denominator? We'll tell you guys not to leave it there. What is the process that we are doing called when we get rid of that radical? Rationalizing. Yeah, we're rationalizing the denominator. Right now, the denominator is not rational either, because a rational number is a real number that is also rational, right? Right now, when you look at your denominators, do you see why they can't be rational? Right? They have imaginary parts to them, which isn't even real. So rationalizing a denominator used to just mean like you couldn't have any of the radicals in them. Now it also means you can't have any like complex or imaginary things in there, because those aren't rational either. Okay? If it's just I, like in part A, when it just has an imaginary term, what power of I turns I into a real thing, a real number, instead of an imaginary number? We just did it a bunch of times, just 2, right? If we can just get it squared. So really when it's like this, all you have to do is get I to be squared. So if you can just multiply by I, you'll get an I squared. And remember, that's completely okay as long as whatever you multiply into the denominator of the fraction, you keep it equivalent by multiplying it into the numerator. So this becomes 7I squared over 8I plus I squared. And we just take all those I squareds and rewrite them as negative 1s. So our denominator will really be negative 7, and then we'll have 8i minus 1, or you could call it negative 8i plus 1 and have a positive 7 in the denominator. Is that okay with everybody? Like very much like the radical, right? Squaring gets rid of the radical, squaring gets rid of the I. But then in part B, you have a problem, okay? What if I tried to do the same thing in part B? I just multiplied through by an I. What would happen in my denominator? The I would become squared, but then what would be the issue? Why can't I just do this? Yeah, then the 3 is going to have an I. So like if you keep doing it, you'll just keep bouncing back and forth between like which term has the I. So what can I possibly do when the denominator is more complicated like this to make sure that I can cancel out the i's instead of leaving powers of i's in there? Look at your multiplication problems above. Which multiplication problems resulted in canceling out the i's? Nicole? Good. We're going to multiply by 3 plus 2i over 3 plus 2i. Do you guys know why Nicole chose 3 plus 2i? She's looking at part D right here where we multiplied 4 minus 3i times 4 plus 3i. And what did we see happen with the imaginary terms? They canceled out. So we can use this pattern that we know to be true. Okay, we have to be a little clever to know that those middle terms will cancel out. So here we would end up with, in the denominator, a 9, and then we'd have a minus 6i and a plus 6i, and then a minus 4i squared. And in the numerator, have a 15 plus 10i, a 6i, and 4i squared. So here we got what we wanted. The imaginary parts cancel out, and remember this minus 4i squared is really like having a plus 4 because it's negative 4 times negative 1. So our denominator is 13. And then in our numerator, plus 4i squared is really like having a minus 4. 15 minus 4 is 11. And then plus 16i. And that's considered a simpler form of that. I know it's a little bit annoying. It's kind of like your grammar rules in English, right? Somebody determined how we're going to set sentences up and stuff like this and where we should rest and where punctuation goes. It's kind of like that with our little rationalizing the denominator in math. Okay? Yes, Emily.